Right, so this is we're going to be about a few interconnected topics. None of them is directly related to something similar, but however, you'll see. I'll try my best to make you recognize many familiar patterns. So a lot of yes, I'm going to build it. So a lot of what I do, we have kind of round curves on the X. And then if we have some curve of some degree, curve of some degree, and then by degrees, and then there's a variable like that. Where this degree that takes down this degrees in H2. And so this variable that since in torus, which is out there to the and then sometimes, so this is given function, and then sometimes miraculously the torus here. And then miraculously, this scalar torus in some other problem, this actually acts in some other variety. This computation, or the human computation, becomes a computation in which this guy actually acts some kind of theorem, the logic so the result you get here interpret this node on one side actually and then double station here. And in this business, there's X check, and people call this check whatever language geology or some kind of century. But if there's also ordinary problems mathematics language for 50-something years ago, and the might also be about something all this time. So to speak, the actual numbers that it comes. That's all. That number is one starts with M. There's a definition, but there's also a complete list of whole global group. So it's either you decide a cube, rational number, or a finite extension. Or you take it to finite cube. And you take functions on the curve that is C times D. And of course, this side that stimulates geometric language and other things. But it's whatever little I know about the subject works equally well for this. But I don't know so much. Whatever they will try to explain, we should bear in mind this. And so then maybe some kind of generality what you like to study is something big, like some machine. It's not essential, like generalized methodologies, it's clear. It's the kind of group that the teacher and then context. The point of the proposal development. Then you want to find a group of the field itself. This is a data. So analysis from. So there's a diagonal identical and then we will also take the other. We will also take it back to math. What is one is interested in spectral theory of mental operators, loss operators, things like that. And what does this mean? So this is the group will take the genes to GLM. And my field is and the first course we started with decomposition GLM. What's this course? This course was GLM. This Argentinian transformation that is reserved for life. So I have the standard classes, these are the matrices. Inside. This is what it means for the matrix they have in the standard base of each end. And then on this side, so that means there is sorry. So this is the so there's for GLM there's stronger implementation that says that you can forget all non-Archimedean places at the expense of taking this federal field in Sept. So this is remain for this non-Archimedean place, but from all the other else, it's only this fact a lot. See all the other places you forget at the expense of the this. And so then what remains from the maximal compact is the problem. So then this double quotient is this is life. So then, of course, we can also take it if we want to play GL by ourselves. Make one change. This is then this can be unipolar. So what is this space? Everybody knows what it is for F. Or we think, let's say F O. this is the upper half plane. And this is the upper half plane. And like that. And then that's the part of this side, that side. This side. And increasingly, you can think of this as parameter, like the way parameter it is you with your instead of you assume your first line is vector, the left is what this is span one. No. Similarly, of course, it's very hard to draw. It's very hard to give a specific complementary domain for integral n, but momentum like that. And so on this basis, one is interested in what? They're interested in the spectrum. And now to there's an action for this. There's an action for and more general, this GLN was maximum compound. This is symmetric state. It has a whole bunch of different operators that being very subgroup or the same proportion. And also the hit calculator, which come from the fact that you can, if you have a lattice, or a function on the lattice, you can. What's a good foundation for the lattice? Now, what is your example for the logic of maybe I'll denote lattice. So if I have a function of left, then I can form something like this. Kind of take out something. Some take out the actual function of left. And I would like to validate it. Then I can sum the value of the function over half. And then this condition here is that I would like this quotient is by group. They'll find it like the side. They'll be finite again in the side. This is a different operator than this defined different than operator. Anyway, so this is like very hard problem to address, to find that spectrum. Unknown thing. But part of the unknown is part of it. However, in this introduction, I also want to emphasize the part which probably most of it is familiar with, that if I how functions. The emphasis is also that you have for functions. then the space, first of all, my maximum compact is just what are adels? Adels, you look at all points, the relations are all points of your curve. And by points, I mean all closed points. And then you look at them, and there is the local field of every single point. And the adels are just product of all these local fields. Your maximum compact are the groups. It's the group over the regular functions of the curve. And then there's a standard reduction, which is we discovered by meaning always people fit this mode. Well, it is the same as endpoints. Operational point all is balance. So then there's a very similar. Then particularly my loop in jail, those are just the spectral vector functions. For vector functions, there's data is a operation, and for any group defines the operation. That can take calculate. Let's see if you what's this. Means are they so this means these are so this is our infinite product over all places. Those are the ones that are regular. So this is so well back here we have this figure which I don't so if I look for Laplace eigenfunction on the curve, there is a sharp dichotomy. There's if you look for Laplace eigenfunction. There is and there are two possibilities. Either this is my so there's a particle code which is like a quantum mechanics. This one we have a free particle of non-compact, and the eigenfunction can be some kind of scattering state, which something actually lives on the continuum. And then or some bound state which is actually lives on the point. We're coming to taking basic constant getting sports. Yeah, I was thinking what is the helpful. I like the basic physical analysis is sometimes called life. But anyway, so this is you will ask for what is the type of function by decay. You can either decay some kind of power inside of curve, or in the case or in case. So maybe in terms of the standard coordinates, that's fine. this. That it's this this white coordinate, it's you can decay polynomial in one, which so consists of the hyperbolic distance can be a local point, or polynomial decay like an exponential decay in distance, or you can decay approximately there. And this was decided by the fact, and the dichotomy is decided by the fact whether you may want to expand your function in some like a Fourier series in this neck, and then so this means your function. And so this is, if I extend it in Fourier series to neck, then the positive decaying coefficient is the constant condition. The decaying my function is controlled by how the constant condition is. This is called the constant. And this decay of that determines the decay of my function. This would be decay. And I'm following and then right. That's what I'm trying to say. So this is the spectrum broadly falls into spectral micro space, so that be direct sum things which are scattering space and this is wrong. And more generally, so what does it mean? Remind yourself what is this fundamental domain saying here? This fundamental domain is saying what is the spectrum tau? Tau is the shortest vector. Which is not. There's actual shortest vector, which is 1. And then when you look at all the vectors in my lattice, which are not in the direction spanned by this one, and look at the shortest vector there. So this dichotomy here tells me that it's so in general, the way the lattice, if I want a lattice to, if I look at the space of lattice, then the infinity, points of infinity in the space of lattice, how can a lattice rapidly change? If I have a lattice spanned by 1, I may assume that E1 is the actual surface. E2 is surface. First one. And then I have to look at where are the, or I can see this one is normal is the second vector. But then at some point I will get really and but it's the case if I have to get the normal. The normal, the third vector can be much larger than the normal. And I look at this, I have this vector order, and the question of how does my line escape to infinity is characterized by where in the sequence I have not just left variable, but two seconds. Like here, if I go to the stop inside my kind of second shortest vector, it's not really the second shortest, but it's not the shortest among those not the sometimes shortest. That gets to do. And so that's what's this pattern? What does this mean? It's like if you have a matrix, you ask for some eigenvalues are very large, and the next group of eigenvalues is large, and so forth. This is this pattern I have. This is the pattern of this parabolic example. In my GL, I think I have something with the first two guys together, then the next group of things, and so forth. So this in general, this is for Gilbert and in general, the boundaries cut of the space of class are verified by parabolic examples. Take L2, and you can take it. You don't have to take it. So let's say really self-proportion. You get to one. One is self-proportion. But for this, you don't need to take the portion of this side. This is first of all, this is red sum of all the subgroups. Modulo certain equivalent to arrangement of association. Association means that if you put the latest subgroups that constitute by the action of the boundary, these could be something about it. Not exactly. And then you have things which you take out two in the functions that come from that. But the boundary of your space, imagine it's stratified by the subgroups, and generalize the fact that the combination of only those ones in the different states and the ones which are kind of like so. This kind of this if you think of this as the many parallels with many body systems, you think of we have in GLN situation, you have like an n body interaction, and then you can have a function which is somehow not too small when this the corresponding particles are close to each other in the pattern in which there's some precision. Like you can have a situation, you can have a scattering, the total scattering state, which means it has some appreciable size, all particles are separate. Then the next thing could be there's some state which decays super fast, all particles separated, but okay, like two particles, few particles. So forth. And finally, there's like a totally bound state, which correspond to the fact that all of them basically together. But that in that part there's a technical way to how do you look at it? What's the projector of this part? The projector of this part is the analog of the formula here. What's this formula there? This formula is this formula here. The way to think about it is I should think of in group theoretic coordinates what's going on here. And in group theoretic coordinates, this integration over F is really integration over matrices 1x1 modulo. You take it from 0 to 1 to really finality. If you take uniform radical. And that's the uniform radical of my subgroup take modulo. So the way to say it somehow here is that this is given by the integral of the function. Integral function over say uniform radical. So for children, we say I have to integrate over parabolic function, and I will have to integrate over all this part modulo matrix. This is the operation taking constant term. Then these are the terms that correspond here. They have one constant term, not 0, other constant term 0. And when you take a constant term, then you get into constant terms, you get into functions, and this part of the so then you get into the operation of constant term. Goes to constant term, integrate that function. And then the Eisenstein series we will get them. So Eisenstein series, they go the other way. They go start from functions all the way go to functions of the group. That's just the operator of functions. That's cool. So we will get to what it really means in a second. And then the question is that okay, in this then the question in the decomposition. So this decomposition is preserved by all positive operators. And the question is, in this decomposition, how do I deduce? The question is, suppose I already know something about the spectrum of my operators formulated, what I already have formulated. How do I find which eigenfunctions of the group arise from this eigenfunction? In particular, part of the decomposition is when the most mysterious part of the decomposition is P, G, those are the capital functions. those are the two of my original quantum mechanical problem that's completely bound state. And in this program, they come and with some kind of black box. We don't know much about them. And it's already true for this particular example. You know, everyone understands the importance. The huge relationship of this. So mass cycle and whatever mass forms, and then what's the actual structure? So such unknown to me. So this is okay. So this is what is now. So Eisenstein sees the way it starts from a linear parabolic to produce an eigenfunction of one. And so how does it? Classical means, the one studied by Eisenstein. Eisenstein lived a very short and life. And there are many things called Eisenstein series. In his short, tragic life, Einstein would study only few instances of general Einstein series. So they will correspond to what? They correspond to group. G will correspond to subgroup. And we have to start with some function on the way. So that will be just function. Subgroup. And since there is a subgroup, this will start with also well, the actual way to relate it to how this X number how plane actually is square root of y. This way will actually scale the y coordinate by 1. It is not so important because the function of y, the starting function of the y, will be dynamic. We start with some function of y. So what does it look like? So I have to write the function over y. So
are you going to give us some analogy with the beginning of the talk? Towards the end?
Yeah. I will sum over all possible frequency values. Besides this one is maybe S.
So you see y, y ranges from 1 to 2.
So y is in the multiplicative group GL1 R. This is so what my life is this would be so with every frequency vector it's negative total frequency, so it's not divided by 1/2. And then the sum of all permutations. But one is about there's some that's shaped by half some consequence, which is one. What's it? First of all, it's clearly a function of one. Second, it's easy to see that it is the eigenvalues seem like I can't remember we will get to that. The exact eigenvalues and programming function will so but don't get your hopes too high because this is never known. This will be always. This is always like for those who taking a quantum mechanics course, they talked about like self-adjoint operators, then the resolver, the self-adjoint operators, and so forth. Stuff like this involves studying solutions of differential equations, which do not like. So that's that kind of stuff. That's like an eigenfunction, which is corresponds to some general component. Eigenvalue is not an L2, but it's not directly going to be relevant to the spectrum. But it is. But how am I supposed to think about it in some sort of generalized sense? And you should think of this as what? As here. Here, what are the primitive vectors? What are the primitive vectors in lattice? Primitive vectors in lattice, especially up to plus minus. Primitive vectors in lattice is the same as well. First of all, it's pairs of co-prime integers up to plus minus. It's also the same as point of P1 over Q. So this is the same as sum of F of Q. And then what am I measuring? I'm measuring quite precisely how big. So how big is my? So I write my point of projected sphere as a pair of co-prime integers, and I would like to measure the subgroup that point. But how big is the Euclidean form of this pair of integers that needs to write point out? I have a point in here, it's a rational number. And I have to write rational number with a pair of integers. The numerator denominator of this fraction. So I can put a point in the lattice. And if I'd like to have a notion of how big is that point, I need to have a notion of the size of the given by the fact that when I say I study the space of lattice, this means I study the space of lattice in Euclidean space, which is the same thing to say I study the space of all possible metrics on the group, in this case Z2. So that's it. I sum over all points to the point. For me, that's just how about double? And I put phi. height with respect to the graph to have a notion for height in the notion of the metric of my life. And that is exactly what my point was. Height of that whole that from here and I will the power minus 1. And now you realize, you look at it, what we just got, just we tend to previously have a report. This guy is actually more speed. She was the F point of that. F point of this. And I get, and this point of discussion, I could have also had the fact that there's this function phi. I could have in principle have some kind of f phi of lambda. Right here, one. But the parallel with the geometric becomes much clearer. If I ask what is there, what's the exact element of this function? What is this? S is the variable. So I'm right, I didn't say what that is. S is really what is this? S corresponds to S. It's a number norm y to the S. This is the character. This is like saying, so in terms of this many box system, this is remember I was trying to say that maybe I was too generous with the picture here. So remember, I thought you should think about this in some kind of situation, some kind of system where there's going to be all that. There. You think of this as being a situation we have two parts of the fine here, two parts of the fine there. But also there is a notion of like separation between them. And that separation between them, if you think of that parameter corresponding to an element in the center of this, there's a non-trivial element in the center of this layer, which takes this one item over here, another over there. So the variable would correspond to kind of like the variable would correspond to in that correspond because there is a separation here, it's the variable that corresponds to well we'll get when we will talk about the expansion so what is the analog of that for function? So, before I go to that element, the situation here, and so this is the general. this is the very, this is the general general treatment, which is some of the point in this portion. The notion of a height, you talk about height relative to, I talked about height relative to a line function. So in general, it will have, instead of being a function of one variable, it's a function of however much is the Canonical. And that's also the Canonical of the space is also how big is the central domain. The line bounds of the portion come from the characters of the group by which you model. And so the characters, the interesting characters in the way are how big is the central domain. So the exact element of that is that we remember we have the analog of the set of lattices. Replaced by Schumann. And then they use G over G. By the space quotient, Schumann. Because you want the G bundle now to have a G more E bundle. And then summation a vector here. W. Try to cheat one. This will be a section. Section. What's a rational number? Should think of a rational number is element of a rational function. Like a rational number in the number situation, it's element of a function, which is a rational function. And so this means that if I have what is a rational function somewhere, it means section becomes from one. And this myself break down now some kind of monotheism.
So we can try that. So what goes to a genome of the lattice itself or the lattice?
So a point, so right, there's the double quotient, which was like a lattice in the number situation. That double quotient really is the space of G bundle. So one lattice is one G bundle. Physical G bundle.
Okay, a lattice corresponds to a genome.
Right. The point is. So this expression here, that just becomes the degree of the description. So, like the degree is like logarithmic type. Say, like some sort of like exponential minus compare the degree. Let's say So the interpretation, degree is literally the group direction, degree is literally the one direction height. And so that thing which from started with degree little, I like to have some curves with some kind of weight like that. It's literally good. And then also, if I have a section, in principle, if I have a section of this, then in principle I can pull back over G mod P. I have of the tautological the assumption I can give it back. The degree tells me tells me what is the degree of this one. But the principle is some bundle. So imagine you're going to Grassmannian. Over the Grassmannian, you have a tautological bundle. Right? In fact, two people. So if you right, so what's a Grassmannian? Grassmannian is situations when I'm in jail situation, my P is like that. That's Grassmannian. So it's like GLN, probably like that. Right, so over the Grassmannian, there are two tautological bundles, the four, the sub. There's one for this group. If I go to the Grassmannian in principle, I can pull back. Not just you can pull back that proportion bundle via my map. So in principle, I get something. It's relatively complicated. Certainly, it's a kind of initial thing to consider. So if I have a cortical theory, that's the principle. If I have a universal bundle in the dark, I can pull it back and consider it as the generalization is that bundle. So this pullback, this is the net bundle. So in principle, I can compute some function over it. And we have, or when we say it has five.
You're just making sure it's close to G on piece, one thing GR five. The tautological condoms of my total or
No, there are two. There's a Grassmannian. You have a Grassmannian KM, you have the tautological K bundle and N minus K bundle. You can pull it back both. So if you have a function of a bundle, you can apply that function. So this Eisenstein series somewhere in the study. Eisenstein series is computations. Eisenstein computer format signal the sheet some bit of S for S and non vector. This is an example sections of this phase one is the basic value you have some according to principal G bundle we have associated with the bundle which is the phase one. So then we can put like a new term, this term here. So type term then we can multiply. Right. Like here, I mean, usually we do computations like this stuff, which pull back a casing stuff close to one. But in principle, you can pull with an actual one. And then you can ask, so it's an interesting question in our kind of reading topic, it would imagine that in some sense, all the sections can be equidistributed in the space of bundle. Like if you so you imagine, well, where can this if I sum in the actual new story, I have maybe I sum over higher kind of degree and I look what are the actual pullbacks of the bundle. So suppose I go to I go to project speed and I pull back all one. So I get a line bundle. I can ask what's the actual distribution of that line bundle in the curve curve. And I would guess that it's equidistributed in some parameter. So you would imagine that there's maybe some global constraint let's say has to belong to this in some manifold, but there's within that submanifold equidistributed. So probably in a new application, you will not so interesting to actually study, but now there's something to study. And okay, so that's a bit after an hour and 10 minutes, we got to the point of actual definition of Eisenstein. So this anyway, so this is what the Eisenstein series. Eisenstein series is a function in a group that you get how? You start with the subgroup, the function of the subgroup, and you start either you count points in the continuous space in a certain way, or you count the section, not the same, you count the section the way you were counting before, but also in some way. And then we're interested in this guy's will span, the series will span will span the corresponding subspace now to group, and you're interested in what the actual space.
These P and you have some subspace you have two.
Right. It's the parabolic modulo some relation is like bundle computation, and then you and then the subspace and then
so it's a for the star, it's the bundle and bundle which gives you a bundle over the curve.
Right. So you have the curve, and you have some kind of G bundle. That if you have a G bundle, you can form. If you have a principal bundle, you can form bundles associated with the principal vector. So you take this G mod P bundle associated with this principal bundle G, which is just mod out by P. So the total thing mod out by P. You mod out by P, you get in particular you mod out by N. So you get the principal M bundle over. So over this space, there's a principal M bundle. And so you can that bundle with the second you can pull back. And you get an M bundle and then so that means you can evaluate the little function on that point. It's like in this light situation, you degenerate the light degenerate, but then maybe some parts of it are light with smaller rank. So you have a way to have a function with the light in a small rank. All right. So what is this again? So this was good, but let's think of what is the size of the transaction. Maybe there's not so much important in the other areas. So what is this guy? What's actually looks like? So this is my log. So what is this? what does it actually look like? So we decided. So first of all, right, but in I was already, but in the line of work that Ina and I do, and other people also do, this sort of setup, which this setup. This setup is super familiar. We always like you may have in any kind of experiment situation. Then we have you want to count curves in the situation. So you want to count curves in something on which a group acts. You always want to start counting curves, not in. So what's the curve? The section of trivial one. Instead, you want to start counting sections of a twisted one. But we always do. This is like the first thing you're gonna do. But then we always somehow twist this just by the maximal dose of the group attack, which is okay because when you get into some ecological computation, ecologically it doesn't really matter if you do the whole group or just maximal dose. We always just this kind of twist, shift operator, then we always say as a function of we never take action in the bundle, we always take a bundle is when the maximum goes in the group. And the idea that here is kind of essential for studying general bundle, what's kind of the idea. It'd be in like in this situation, like this very situation, I think we like take people like we take people to Burl, like around. You would have something. So for us also, I kind of think that it's not so ridiculous to ask for what is the Eisenstein series to bring it here. So this Eisenstein series is going to be back, so it will be a function of one variable. And of that function of one variable in the correct word is going to be like a rational function of one variable. So it's going to be something. So then for so this is the color on here. So this is the characteristic in this characteristic field, and that might be equal to cardinal here. Then the result that comes that was important. The result will be a rational function. For us all two, this will be a rational function of 2 to the s. And that's not ridiculous enough. What is that function?
So you there are possible Chimano?
Yeah. So for you have some curves. You have one of these GL21, SL21, for every point there's some rational function of Q to the S. That's not like if it's actually if that bundle is some of two line bundles that directly relates to the shift operator, like to study. But if it's not, we're at some of two line bundles. Then it's something like so anyway, I told you that the map this Eisenstein series, the way it behaves in the class is dominated by the constant term. And the constant term, I moved my notes for that. Hope I get it correctly. Different notation. Well, I hope it's correct, but I think it's going to be like y to the power plus this plus so don't hold me accountable in this notation. And then there will be, this is, so, but I told you it's going to be like, like quantum mechanics, there will be like incoming and reflected wave. And so here will be reflected wave. And then the interesting thing is this reflection topic. Another reflection topic. Like that. And that's this particular computation is relative to Mass or Hilbert, but Lennon's proved the general stuff like this. The general pattern, there is some plausible action. So this is, I told you this is like some kind of bunch of particles interacting via some kind of value of various interaction. And there are terms which correspond to different terms. Here the value is just same kind of, and this coefficient here, it's like 5 so ever since it was computed by, like I said, people of course couldn't stop thinking about whether by just quantum mechanics, just doing some kind of quantum mechanics model system, can I say something about the series of this function? So far we have discussed it, and I don't exactly advertise and think about it. Especially capitalizing, but people have thought about it before. Pretty smart people. Yeah, somehow the best you can currently do is to prove like a. It's not super. It's talk about another one. It's talking about the fact that if you look at this, then you see that there is. So like the volume growth. It's very easy to check it because you need to know how the hyperbolic volume goes to y, because this you see this is never going to be an L2 because if you take L2, then the worst term will be the cross from here. This will grow well. Even if you make one exponent small, the other will be large, and the cross term here will be just 1. And that has to make the integral just exactly divergent. Now we have to remember the volume of this modular figure, it goes like y, or it goes like 1 over y squared. Like 1 over y or 1 over y squared. Anybody remembers? You know, you have your general example. Anyway, it's not going to be other.
Okay. Where?
Right, so. So that's so this is let's assume this, right? And so then so then the conclusion that you can never make it exactly, there's no value of f that will make it normalized. There's never no. However, if f is a I times r, this is kind of borderline. So in fact, this would be the but there is one more case, and namely, this is about basic properties of the Riemann zeta function. Riemann zeta function has O f and this equals 1. So in principle, it has both poles. So this, you think of it, that this is this expression has poles of 0 to 3 to the function has poles of 0. You think maybe the zeros of the function is important here, but in fact they are. And so this is the only thing that is actually important is that they have a pole. So what would that be? Pole of s equals 1, then you're going to get a function which is just y is 0. Because if you look at the pole of the function, there's the pole 1 here, minus 1 is okay. Nothing happens with minus 1. So the residue would be just this guy evaluated as 1 like 0. So what would be the eigenfunction with the same eigenvalue as y to the 0? Well, we have to do the constant. Then this is the constant. In fact, the constant function, the modular figure would be in the finite volume, using back human. Actually, but there's a continuous spectrum of this. In this, so what I was trying to explain, like finally, you can eyeball this reflection composition, and you can decide just by eyeballing it, you decide that either so if for those there is some sort of human proof like actual quantum mechanics, or maybe you took some kind of integral system course that goes through the analysis like the spectral analysis or some related thing. You would know that if you look at the reflection coefficient, you can conclude something about the spectrum of your problem. And here the conclusion is that there's a continuous spectrum. There's what to be imagined around here. And there's one piece of the space that is one function here. And this is generalized response. So generalized for this. This piece of here, generally, but not in general. So if I have this piece of has something to do here. But this is not something to import in this element. Well, in level 2 to do this, someone one of two and the input out this guy can put 0 input down, and this guy can put input down. And the general principle is supposed to be you don't stay there. This is an open language which architect what how the system is. So the actual theorem. This theorem has history. So Langlands itself uniform groups. And that's what you can do, like around 1964. Then many people using the results, and then I don't know how to check out also. There's some kind of way to abstract it, which I could explain to anyone. So finish explaining that. So in their symmetry. So that says that the pieces of that the following. This is the pieces of that. So this is for P. P. And so one. We now explain how does this generate that the piece of space for the following fact these are related by both and then you look at solutions. Actually, Q times sometimes I thought you could say that my x will be an element in either the real algebra or depending whether this is in the number field. And then I move to the equation the action of x on my element theta is equal. Well, it's either theta in the first case or 2 times theta or and in case of Q, or in this case, in the functional case, this is Q. And then, so then this means I can write, there is, like this means I can write x equal 4 x some kind of characteristic of the element, which is there's a canonical, for any component is canonical by Morozov, by this is SL2 triples, this is Morozov, so there is this Jacobson Morozov, and times something in the central line. So the central answer here I'd like to take time. There's a canonical thing, there's a time or something. And then I just take the image, so that this x being canonical either here and there, then this x here. This is this one. So that says that the spectrum is given by the constant supply in either the fundamental group or the algebra. And then I say, well, this in this fundamental group or the algebra, I look at Jacob Morozov, times the compact for the central line, and that would be so. Let's do it in this example. In this example, the 2. There's the 2 plus the either. Then in this case, this my model is, well, let's say the function is in this case 1. Let's take the real. Then it's just 0. And then the compact form of the centralized is the whole thing. And the compact form of the centralized is the algebra is in fact, exactly R times yes. So it was a compact field, compact form. The algebra is natural imaginary numbers. This mass, this one-dimensional thing, it's the Lie algebra of S over T. By contrast here, this is here in this X that becomes 1 half zero, and this is 0. And it is multiplied into confusion between IS. Then this is as either pure imaginary or one. And more generally,
This is the statement of the
statement of the theorem is that you're interested in the spectrum of the algebra generated by, let's say, so we take the algebra generated by n-dimensional operators and take the operators, and then in the function for case just and by Satake isomorphic, they lie either in the context plus the group or the context plus the function. And then I take the whole. So with the context plus the time, you look at the element, you look at the corresponding vector from your own elements, and then you take that and you take anything which differs from it by the compact subgroup in the central line. Yes.
XJ is the simple element of the principal element.
That's right.
And the compact central that's the central element.
You look in the central line before the element, there's back for compact subgroup, which is and then you look at the
and this the other X these are
this is the condition that it has to be. If you look at solutions of this equation, there's a canonical one, and then the first. If it is the case that you have two different X solving this equation that is different by a centralized element, and so you require that this element of the centralized line is the maximum.
We offer is that's a practice, right?
It's an action.
Yeah.
Yeah. You know, in either case, the central and the algebra, by this little adjoint or the big adjoint. And the general state should be okay, for example, the general statement is that so general conjectures, those come from right? Yeah, it's something might look like you can't name all the great people for words and that. So I apologize for what you just said. If I don't somehow the great conjecture by Davis by people. They say that in general, this representations Like, so the representations, automorphic form of the group G have something to do with representation of some other, like the color, in the language group. So in particular, in this situation here, we need some kind of language group. The slightly material. It was like it, so for function field K, that's the guide for the number field case. I simply don't know much about it, so it's some kind of enrichment of the function. It was like this to go here. But in general, if your loop is not exactly split, then this is not. Anyway, there's some kind of stuff. This is just the node of the loop. And then, for example, it's good to start. So in general story, you can start with situation where this is temporal, meaning this already goes to something compact in here. And then you would like to the way this is given to the example, this is now you take with your group. And you would also just have that too. And you would like this to go to the whole group. In a way that so this segment group is something extension here. So this is from language group there's a canonical by effect, canonical level. And you would like that. So this is SL2, it has to do with the principal SL2 triple from that element. And you would like your the action of that set quotient to be whatever it was here times this representation. The new representation is supposed to be whatever it was here, and then you also go here the set, it goes to just this. Let's say the function from here, let's go to so this maybe I'll try one more. So the fact that you trade the new quotient element and the Jackson-Morello, that you just trade for SL2 representation. And the fact that this guy here, so this was it was part about the centralized. It was part about this parallel code. And here, first of all, at the beginning, this SL2 was just communicating. First, there's some part of the predicament, there's some part of life in the centralized, but it doesn't communicate that. There's also some part which is scaled the canonical by here right now. So now, how is one supposed to get there? And right, so now we have to somehow try. Here. Yeah, right. See, the exact analog of it. He said in general there's some general is maybe I'll write it in the analog of that. This is, again, this will be dominated by this counter. The way the counter is going to be summation, some stuff that Subset has to do with the fact that only some subset and dividable will normalize your living subgroups. And then there will be, it's not only defined by the double, but there will be an action of, will be this kind of double acting one word. You started with your function. You started with your function, whatever function we had below, it was 5. And then we can further multiply by 1 to the speed. At the end of the program, like we have the cube program that has to do with when you define, right? Remember when we defined the Eisenstein series, there was summation with like some notion of time with something like that. And then here, some kind of direction coefficient that has to do with some general kind of ratio. We have for us all and one and only God. It's the function in general something like that. And so this is what that. And then you can try to infer the spectral from the same way as you would just work. So somebody tells you that these are the eigenfunctions which are not exactly normalized, and you would like to infer the actual spectrum from this expression. And you go about it just the way you go about it in quantum mechanics. Quantum mechanics, the typical approach is some kind of integral. So, like, can I see the show hand again to the quantum mechanics? No, that's not so much. So if you have, so what that is, I think it would be that while these lines are eigenfunctions that may normalize them, one can try to form something normalizing by working some kind of way to take it out of this. And so that would be, and then you would pick, you replace this guy by something like you integrate the net. This is you take this is now and you integrate it over the real part. So the real part of that is something. And then there's some function, some great functions that are out. And if you take this function nicely, then this will be a normalized way, right? It will not be without the mathematical function. And so then you can rephrase the problem of extracting this equation as somehow to extract the equation, you need to compute some kind of these are relevant some integral with that sort of the reason that in this SL2 example we thought about the residue because it's the systematic way to do it. You do you can write down integrals in which the derivatives would be described. It's too late. Yeah.
So when you put the GL1, to just describe every element.
Yeah, exactly. That's exactly how it's done. Exactly. So then you think, how hard can it be? You know, it's just relative, it's a integral, like temperature fluid. And it's fun. I mean, like those themselves did the G2 thing. Integration of G2 to the double. Okay. G2 has the product is roughly over roots, which is like the double integral. Takes like 30 pages of spectacular computation by references, and he kept us right. It's kind of amazing. It's just up to the name somehow. You know, you read the book, and it's like 30 pages of tables of various references and so forth. It's not an elementary function, right? I mean, these references are not elementary functions. And most of them, the integral has a billion of references, most of them cancel out. And so G2, to remind you, G2 has G2 has a feature, and then it has so then those important elements. G2 doesn't have so many important elements. So every important element is classified by the largest limits of all of the. And so the classification of any important elements in every P group, P algebra can be used to important elements in smaller things. Modularly, it can classify them in distinguished ones. Distinguished ones are those which are not contained in any smaller, right? And G2 is the first P algebra that has an interesting distinguished element. It has an interesting distinguished fact. So in G2 there is a principal and this. So in principle there is, I forgot how many references are in this integral. I mean, there are 12 roots, and they can, you know, these are L function over roots shifted by summits with the 12 roots. You shift them, so there's tons of intersections. Most of them actually give you 0 references, but 2 give you the right thing. The principal involves all the people, the whole street market. But then sub-principal involves there's one and only reference which is non-zero, and it's not a function, and the one that gets it right, and that's something that it's like this hunters and gatherers. The hunters and gatherers were able to somehow process in their minds so many natural phenomena that we now require us to use computers to do. Same thing in math, so just to generate because we were able to do this. Anyway, that is not easy. That is not easy. And to relate with something else, to do it not easy is where else in this seminar do people compute some kind of integral with some sort of function that products over roots and shifts over. And that's a very familiar subject. It's like solving using the logical equation by an integral, something like that. And so if anybody ever tried to do this, you quickly realize that these computations, they're really hard to do without some kind of geometric guidance, because you're in an already relatively small rank. You get so many of these references. Most of them have no bearing in your actual problem. Most of them are just the artifact of you writing an integral in some particular form. Most of them have very little bearing. And so to cut the long story short, and which I have to do this time from the cow, is that some kind of good line of thinking about like the most theoretical has been to think about them geometrically, meaning that this integral is just result of localization of some it's like this Riemann integral. It's a Riemann integral. And the way I think about it is it's this Riemann integral is really just some kind of localization combination of some geometric stuff. Then you have a better handle on it. And so then, so the starting point for demon for the part was localization of the integral. What is this? It is just localization of some topological. And so now it's going to be just like in the beginning of the talk. Here you have these intervals here. They're just like so this is the beginning of the These are the ones that do this high computation, this real computation. And now they will be just the covariance variables in the set. And some covariance integral over what? Over things like over so just write it down and then talk about this. Over some kind of potential finding. Well, potential problem is option. Depends on your interpretation. So let's take the function. Think about it. Or what? We take the rule. This is what's written here is what's been potential triangle for motion. Both the long integration way out. So and the main point is that this guy, this is some kind of intermediate material over the dot. But this guy here is by itself. It just stays itself. Doesn't matter what you integrate here. Just stays itself. What is it? So this stays itself. It's what? So what is T star? What is T star? T star function might be is it can appear. It's a Borel subgroup. And we'll go to development. And so this thing here, what is it? So you think about the moment and the condition. This part here is really that's just really open. So this guy here, you can think of it like this. So this is really disjoint over eta, where eta. This relates to the importance. Important elements. Or the rank on the condition. And then you take what? You take so there is if you want interested in Borel side which containing the that's the Springer part of the eta. So if you go to the Springer in the since you took the loop square times the slide. And whatever whatever the integrand there, we see that you're going to, in the end, you're going to integrate it over, in the end, there's a portion by the center. So first of all, there's a sum, whatever it is. First of all, there's the sum over the portion. Second, the sum is going to be, so this is some kind of stack, and this is also stack. This is stack here divided by the centralized of this own key. So this means what does it mean? It means in the end you compute a Riemannian integral. So what does it mean integrator of a stack? It means you extract the invariance with respect to group maps. So that means in the end you're going to be integrating over the maximal compact here. Is correct. The line integrated with the spectrum, you will be integrated over the maximal compact with the centralized. And then this would be this guy, that would be the spectral projector, that would be the spectral measure. So that's yeah.
That's slightly the G, that's the constant.
It doesn't matter. It's just we reached it only in the we don't need the global. Just locally. And so now as it stands, of course, the natural question is that so how does it relate to the fact that there is what I think is the beginning, then I can point to two kind of slowness features defining the answer, but not defining it. I can point to two features of the answer that resonate at the beginning. At the beginning, we needed the scalar values to become correct. They really are correct. They're really variables. It really comes from this improved Torah. And second, the fact that so you can ask what about the I had some kind of curve counting, but one time no, it's just completely classical. The other side, the reason I had a completely classical on the other side, because on my direct side, I'm only here for the spectral analysis, I don't need the whole Eisenstein series. I need just to pick one aspect of the Eisenstein series to count the chair. That is the reason why I'm not seeing any kind of quantum information. I don't see any kind of curve quantum information. Just a class. All right, so I'm well over time actually. That don't have the sound. Let's be strict.
How much of this do you think is quantum physics? Like, out of kind of physics. Not quantum.
Yeah, I think it's it. I mean, you can like it's real.
Yeah.
I don't know. I think it's complicated. It's complicated. I thought it's going to be easier because in the end, this.
It could be something that we haven't discovered, like
No, I mean, very, very naively, you think of this problem about like null representation and so forth. There are really down to down type problems because there's really, there's a whole bunch of literature which started with maybe Berkeley or other people. I just said, well, my head is how a non-algebraically closed field is like a three-manifold. I think the three-manifold are kind of cyclotable three-manifold, which you're, and so then So the kind of curve counting we're doing here, that's more or less super close related to actual problem. I mean, this kind of the kind of counting that we really like to do. And what bothers me a little bit here is that this you know, this kind of here is not really, this is, you know, this kind of here is, you know, first thing, the DDU is this RG1B, that's this RG1B. But I have a little bit of, I mean, I couldn't really connect it so that it's just really actually clicks. But I think it should be doing it. Should be doing it somehow bring it in a way that is that actually actually matches the purpose we like to make research. And it's close. I thought about this for some time, and I'm pretty unhappy with the ideas that not exactly.
So people who know Lebanon have been telling me is that we haven't quite studied the thing that they really wanted. They wanted a slightly not the kinds of, so I guess Lebanon relates to conformal field theory, and we understand. So first, I think the encouraging thing is the fact that this has flavors of 3D mirror symmetry, which suggests that it does connect to string theory and not just conformal field theory. But even in the conformal field theory world, which isn't real Lebanons, we haven't quite connected to what they would have liked. And there's some other kinds of questions which naturally does arrive from string theory, which we haven't landed on. So it's possible I want to understand if that's right, then maybe that might be the missing link.
It's far
It's kind of things that Nikita is funny circle defects that look very less elegant than what we have, but somehow they're more amenable to language time questions, and maybe then you can end up with slightly different looking theories, which might look more like that than what we have. Our story is a little too big for them. There's no bundle on it. The bundle is somehow. Then you have conformal blocks, but they're not conformal blocks coupled to a bundle.
You know, conformal theory is not, maybe I'm not thinking the right way, but I'm not thinking in terms of genetic language at all. I think it's the relation to that genetic language. No, so
Yeah, no, I know.
Yeah, but it's what I would call the most fun capital. It's not the most fun, but imagine what is that thing would be even for you know, what's that what are the other terms of this expansion? So the other, this is the constant. And then the other term, even for the let's say we stick with the minimal particle because the other term would have still some kind of Jones expansion here. So maybe let's say we take the portion, right? So we take and this part. And so then the other terms, this y is the analog of this y is the analog of y is some sort of generalization of pi, have to go this way. And then what's the generalization of the x coordinate? Because when you go the x coordinate, you need this, upper triangle or whatever. R, upper triangle times the norm, and the upper triangle. This sort of thing. And so for GLM, that would be, you need like n choose 2 variables. And so how does this n choose 2 variables? You need some kind of function. So there's the diagonal elements are the diagonal elements are your scalar variable. So this the derivative of function of kind of like an upper triangle matrix. Diagonal elements are your scalar variables. And the other terms are some functions of so many variables, in which what I find it hardest is what would be the match to some kind of supply variables we have to count inside. Because there's some part of the clearly got up. I said this is supposed to exchange scalar for covariant, covariant for scalar. So this is kind of like a scalar. So sorry, this is some kind of variable that's supposed to go to some roughly scalar variables. On the other side, but some more because you can instead of n, you have like n choose two. So I have difficulties to like for SL2 for it. For SL2 that works pretty beautiful because this one variable here, which is on the null side, is exactly the degree variable. It's exactly right. You don't need the you can have a non-constitutive relation to this formula, but it's exactly but then beyond that, I was a little bit complicated. That is what we only want to begin with. Maybe in other words, so maybe okay. Hold on, just erase whatever. Whoever says somehow, whoever can erase what I just said, you can just erase it. And the main difficult, even within the conventional PhD university, I have very difficult time thinking about what would happen with the non-abelian part of the equation. We're very good at thinking about various tori, but about the non-abelian part, as far as I know, we don't really know where that stuff is supposed to go. So this is, in principle, if you're interested in some kind of, if you're interested, so suppose we're interested, I have this picture here when you have some kind of curve calculus in geometry. So for those of you who have to know, so in principle, we would come to some kind of curve. In some geometry X. And so then in geometry X, there could be things. There could be a really non-abelian group GX and X. And X, and also over X could be a quotient by non-abelian group. So there could be a really non-abelian, tautological group possible over that X. And when we do the curve counting, we can do the usual things. First of all, we can count sections of a twisted X bundle, which is twisted by real numbers. And then we also can pull back the principal model, which is really not somehow weighted by the function of that time. So both the credit and the killer variables one can really take non-abelian. And then the kind of computation we use, that doesn't matter. It's kind of out of the wash. But if you, in principle, you should be able to do that. Like, I mean, if you have, like, if you count sections of some kind of twisted bundle, this is not just a number. This is some kind of whatever topology, whatever, some kind of material class on the moduli space of G bundles. And we've never explored that. We always use just doors. And then so that is maybe this is actually the most practical thing in terms of relating, because the whole truth in this story I was trying to think, the whole truth was and this is, to the best of my knowledge, this is not something, it's certainly not something I understand. I don't know if you understand that. Where that not to do itself, because we're going to remember this.
And this is the non-abelian part of the gauge group, not of the flavor group.
Both.
Both.
You can write both.
Right.
Both of them have non-abelian of the stuff. And what is that? What's supposed to happen with them? Yeah.
There are questions. Okay, there's another question.
Sure.
So